Hello, my name is Rick Crosslin, and I work with the AMA, the Academy of Model Aeronautics. And it's my pleasure today to share with you my love for science and for making, flying model airplanes. So I'm a teacher, I've been teaching a long time, and I like all science, but I really especially like the science of flight. Now I know in your camp, you're going to be making some pretty amazing models. You're going to be learning how to make them, how to trim them, and how to fly them. Over the years, for me personally, when I learn some deeper and some additional information about my hobby, it seems to make it more enjoyable for me. And so I hope today during this little workshop that I'm going to be able to do three things. I hope I'm going to be able to tell you some things that maybe you already know. I can reassure you. You probably say, oh yeah, I know that. The second thing I hope to do is I hope to tell you something or show you something where you go, wow, I had no idea that that would work. So I hope to expand your mind and give you some other things to think about. And then the third thing, since I am a teacher, I always like to say one thing that's completely false. And maybe you'll pay attention and figure out what I say during this presentation just is not true. Or maybe you won't. Or maybe me saying that I'm going to say that is the thing that's false. I'm going to leave that up to you. So let's get started. There are a couple scientific concepts that will really help you understand how your model and all aircraft fly. The pursuit of flying has been going on probably since the first man or woman looked up and watched a bird glide or fly. Or maybe when they saw a seed, a whirligig seed, maple seed, fall out of a tree. I don't know if you're like me, but I would like just for maybe one day be able to fly and soar like a bird, just to experience flight. And over the years, many people have done that. In fact, I used to live and teach in Cairo, Egypt. And when I went to the museum in Cairo, there is a small wooden carved glider that probably some pharaoh's son or daughter played with. Of course, studying birds. Also, for example, scientists like Leonardo da Vinci, the famous Renaissance scientist and artist, he studied flight. He studied birds and their wings and how their bones are hollow and how could they possibly fly. He did a lot of cool experiments besides dissecting birds to study the anatomy and how their wings were shaped. He was credited with the first parachute. A parachute, it looks kind of like a pyramid of Egypt, the Da Vinci parachute. He also made sketches of ornithopter. Ornith means bird, a thopter, maybe you might say one of the first helicopters. So people like Leonardo da Vinci, the Egyptians, and even some of the Greeks, Icarus, and who studied flight. And of course, you know the warning, listen to your parents, because if you fly too high too early, you could end up with melted wings and not a good day for flying. I will tell you one thing I learned with the AMA in building models. Every model you make will probably crash and you'll have to fix it. And for me, that's the learning, to figure out what went wrong and to try to change a variable to improve it and make it better. In fact, that is the scientific and the engineering endeavor in our world. To see a problem, test the different variables, and try to improve the outcome. And so you're going to build planes, you're going to trim planes, you're going to fly planes, and you're going to crash them. And whether it's a model plane or a full-scale airplane, that is some of the very same strategies that everybody has done. Now you move a little bit further in the history of airplanes. We had people who studied how hot air balloons flew. The Montgolfier brothers in France were the first to send, with the backing of the king, passengers into the air. And of course, the King of France, he did not want it to fail with his name associated with it, with someone being hurt. So I believe the first passenger on a hot air balloon was not a person, but I think it was a rooster, a dog, and maybe a goat. You'll have to look that up. Maybe that's the lie I was telling you. But I'll tell you one thing. They used to think that there was something in the air, some magical property that allowed it to fly. And so not only did they make these big silk balloons, but they actually put a special recipe of things they would burn. Who knows, even like old shoes and garlic. But we know today that it had nothing to do with the things that were being burnt, but it had everything to do with hot air, the air that expands and rises. Hot air balloons. Now, if you think about that, you never want to fly in a cold air balloon because, as you might imagine, hot air balloons go up and a cold air balloon would go down. Maybe if you're visiting the Grand Canyon. No, bad idea. So all of these concepts, as the French explored hot air balloons, there was even a time when they would think whole cities could be able to be part of a hot air balloon in armies, but that didn't work out so well. And then we come to people like the Wright Brothers. And one of them was born here in Indiana, where I teach. Now, the Wright Brothers were two kids when they were growing up that actually were kind of mischievous, and it's a good thing that they turned to science because they used all their energy to figure things out. And one of the things they figured out, of course, was they made a lot of bicycles and they improved upon bicycles. And that skill set of being able to build something and fix it helped them be the first in flight. Now, there were a lot of people around the world at the turn of the century that wanted to be the first in flight. If you ever get a chance to visit North Carolina, you'll see on the license plate, first in flight. I have to tell you, when I first saw that, I didn't pay much attention to their license plate, and I thought it said first to fight. And I thought, man, these people in North Carolina, they're first to fight? I better be on good behavior. It wasn't until I had a chance to visit Kill Devil Hills on the coast of North Carolina, where the Wright brothers did their first successful flight. Now, if you think about the Wright brothers, they wanted to fly. Now, to fly, there's a couple criteria. Number one, if you just jump off the roof like I did when I was a kid with an umbrella, you're moving in air, but you're not flying. So the rules were pretty simple. You had to have a heavier than air, so you couldn't have a balloon. That's a different type of flight. You had to be able to take off from the ground. It's not flying if you just climb up the top of a church steeple and jump out like a monk did in England and broke both of his legs. It should be powered with some sort of an engine. And the Wright brothers were given a giant chunk of aluminum from Alcoa, and they used that to make their machine, to power their Wright Flyer. Now, they also needed two more things. One of them was a pilot. Putting something together and shooting it into the air, not flight. So the first flight had one of the Wright brothers actually in the Wright Flyer. And the final, and probably the most important part that you'll be interested in, is it had to be controlled. Controlled flight, meaning it should go where you want it to go, according to the variables. And if you think about an airplane, if I use my hand, has three different ways it can move. It can move a roll, it can move a pitch up, pitch down, and it can move a yaw. So these three terms, roll, pitch, and yaw, are actually nautical terms. Before airplanes, going in a boat or a ship was the way to go. Even the sailboats still used air to go. So a lot of the terms you hear in model airplane and full-scale aircraft has the French words or words associated with boating. And why French? The French loved the pursuit of flight, and many of their early pioneers were French who tried to figure out this controlled, piloted, heavier than air flying machines. Now, models today are used a lot because a model is a part of science that can tell you how an actual event, phenomenon, or machine might work. So we use models in science a lot, and you're going to be building models. Now, the one thing I'd like to share with you is that all models have limitations. They can do some things very well, but they can't do everything like the regular phenomenon. For example, every time you watch the weather, that is based upon a computer model that has all kinds of variables, temperature, air pressure, and all sorts of seasonal things that go into the model. So you'll be making models and you'll be modeling engineering and science. Now, we talked a little bit about some of the early pioneers in flight, but one thing that we also mentioned was air. They're called airplanes. They need air to fly. An airplane could never fly in space or on the moon. There's no atmosphere. There's no matter for it to fly in and against. So air is pretty important, and a brief understanding of air might help you. And so I brought some things today about air. For example, air, the big three things are its temperature, and its direction, and its pressure. So you might see something like this if you're out flying planes. This is a fancy name for an anemometer, to meter. So if I turn it on and I blow it, and it actually can show you wind speed. A weather vane might show you wind direction. But I'll tell you, the cool thing about air, no pun intended, is air is made of matter. Now, you guys have probably studied this in school, but I'd like to share with you matter. There's two things about matter, and I call it the Arnold Schwarzenegger and the Vanna White of air. All matter, whether it's air, water, rocks, or this desk, all matter have two properties. Okay, the first property is all matter takes up space. When I say takes up space, that's my Vanna White, because she's always takes up space. So all matter takes up space. For example, this pair of scissors, it's made of matter. It takes up space. I can't put my finger where the scissors are. This styrofoam ball takes up space. This roll of adding machine paper takes up space. And so matter takes up space. Even if I wad it, it still takes up space. That's the first property of matter and air. Air takes up space. In this balloon right here, no air in it. Takes up space. Now, the second thing of matter is all matter has mass. That's my Arnold Schwarzenegger impression. So all matter has mass. And so mass is a fancy way of measuring how much stuff is in an object. It's not weight, that's different. Weight is actually a relation to gravity. We can talk about that another time. But mass is how much stuff. So for example, this can right here of seltzer water has a certain amount of mass, about 400 grams. And if I took this to the moon, the mass would be the same. If I took it to Jupiter, the mass would be the same. Now the gravity affecting it would be totally different. So if you used a scale, gravity to measure, that's actually measuring the effect of gravity on this object. And on the moon, of course, it would weigh 1/6. And on Jupiter, if you could weigh it on that gas giant, it would be basically 400 times the weight of it on Earth. So gravity and mass and weight are all connected. But all matter, repeat after me, takes up space and has mass. So air takes up space and has mass. And a lot of kids talk about, like, for example, I have this piece of paper here. It's made of matter. So it does take up space and have mass. Now the mass may be so small, you can't tell the difference of it. But like one piece of paper is so small, it's kind of hard to tell. But if you had 500 sheets of paper stacked, you could feel the mass on that. So just because something is small, that doesn't mean it does not have mass. And if you look around my room here or your room at home, almost everything you see has matter. The walls, the desks, the computer screen, the carpet, you, me, the table, all take up space and have mass. So sometimes I like to challenge people. Can you think of something in your room that does not made of matter? That's a tough one. I'll give you a hint, like a smile, an emotion, and maybe even a sound is not made of matter. But most things are. And your models that you're going to be making are made of substances called matter, and they have different properties. So air is very important. Now, air moves, and when you're out flying your planes, it's very important to know the direction and the types of air pressure. Air pressure is nothing more than, we can pile a bunch of air together, and since there's more air, more mass, more pressure. Like I showed you on this balloon, hardly just regular pressure, but if I blow it, I'm increasing the pressure. I'm putting more air into an object. You probably know this, but if I took this this glass right here and I filled it up with water, I can't compress that anymore. Water barely can be compressed. That's a good thing. That's why we have hydraulics. When a machine on your brake on your cars or a front end loader, that has a liquid in it with a pump that pushes a force, and that force is translated to the other end. So liquids cannot be compressed, but gases and air can. When you pump up your tires, that is adding more pressure, and we measure that in PSI. Now, here in Indiana, I, believe it or not, am about, I think about 700 feet, I used to have it, above sea level. And if, of course, you live down in Florida, you're at sea level. And so the higher you go, if you live in Colorado, you're higher on a mountain and you're above sea level. So if you think about that, all the air from here to the 50 miles up to the atmosphere, that is air pressure, the press of air. So that makes me thinking that an airplane might fly differently at sea level than it does in Indiana than it does at Colorado. And I'll tell you what I notice this, because I like to use my science to observe things. If you hear me say something, the first thing you should do, scientists and engineers are skeptical. That means we don't believe everything we hear. We like to see it. And so what I thought, well, I wonder if I took off in an airplane from Denver, would it be the same thing as flying here in Indiana? And I observed one time that when we were taking off at Denver, we really had to go farther and faster before we pitched up and took off. And I asked the pilot about that. It's because there's less air pressure. There's less air pressure, meaning you have to compensate that with maybe a bigger wing or go faster. Now, if you think about this, it's one of the coolest models ever flown. Happened 2 summers ago. And it was a very special helicopter. And it was at a very special takeoff and landing spot. Talk about RC, remote controlled. We had the first ever helicopter take off, or rotary copter take off from the surface of Mars. Now, think about that for a second when I told you about air and air pressure. Mars does have an atmosphere. It's not oxygen and nitrogen, it's mostly carbon dioxide, but it's a lot thinner. In fact, if we went not on top of Mount Everest, and not in Indiana, and not in Florida, but what if we went somewhere like super Death Valley, where it's really went to the deepest canyon on Earth? If that would be more pressure. But what if we went up by Mount Everest, where the air is so thin, it might be very difficult for a remote rotary vehicle to fly. As a matter of fact, that it is. Have you ever seen any videos of helicopters trying to land or rescue people on the tops of mountains? It's very difficult. Not because it's slanted, but mostly because the air is so much thinner. So how would you compensate that, knowing what you know about air? Well, there's two ways, and they did this on Mars. Number one, you can make a bigger blade, longer and thicker, that it can interact with the air. And number two, you can spin it a lot faster. And that's what they did on Mars. It's so cool to see those videos. And that's why you can't fly a helicopter on Mount Everest to rescue anybody, because the air pressure is different. Air pressure, or the press of air. Now, you should know that, because especially if you're flying free flight or gliders, knowing about air and the types of micro environments around you. So think about this for a second. Where does wind and air come from? Most kids said, oh, it comes from out west. Because if you watch the weather, it's usually blowing from the west. But actually, the weather and the air and the wind basically comes from the sun. Yes, from the sun, because of the uneven heating of different types of matter. You're probably thinking, what's he talking about? Well, if we have the Earth that rotates, and it's a good thing the Earth does rotate. If the Earth did not rotate every 24 hours, we would be in trouble, because the side that always faced the sun would be super hot, scorching, kind of like Mercury or Venus, and the part that was away from the sun would be super frozen, like the moon or Pluto. And we'd only be able to live on the very small margins. But because the Earth rotates, that means on its axis every 24 hours, we can heat up and cool down, heat up, cool down. Those are cycles. In fact, if you observe the world, our world is filled with cycles. Hot, cold, day, night, life, death. We have all these cycles that are pretty cool to understand. So, wind comes from the uneven heating. For example, I have this candle right here, and when I light it, getting back to our hot air balloons, when I light this candle with the, if I can get it lit here we go, you notice that the smoke and the flame goes up through what's called convection currents. So let me light this candle, and now I'm heating the air, and the air, the heat, I can feel the heat up here, no heat here, no heat here, because when it gets hot, it expands and moves up. So now we have this sun that's doing billions of chemical hydrogen crashing and giving off all this energy every second. That's hitting the Earth, and it's warming it up. Now, what's cool about this is that the oceans and the land warm up at different rates. There goes the smoke going up. That's kind of cool. So what I mean by that is this. All day long, the sun heats up the ocean, and liquids are really slow to heat up. But when it's nighttime, they're very slow to cool down. So their heat capacity is different. Slow to warm and very slow to cool. Land is different. Land heats up really quick, and particularly depending on the color of the rocks or if it's grass. Man, when I was a kid, I used to live out in Arizona, and I used to like to go barefoot. You don't want to walk on the blacktop road in the summertime in Arizona. It is so hot. I remember, and running to the shadow of a car to put my feet underneath there. And then the bad thing is, in Indiana, we can just jump in the grass because the green grass reflects a lot of the heat, whereas the black asphalt absorbs it and heats up. Of course, in Arizona, there was no grass, and if you jumped off the road, there were all these stickers. So don't go barefooted in the summertime in Arizona. Now, what does this have to do with airplanes? Well, that uneven heating of a giant chunk of air that slowly warms and another chunk that quickly warms causes this uneven thing, and nature likes to be even. So if you have something high here, it's going to move to a low pressure. And if you have something low pressure, it lets other things come into it. So that's why we get our wind. Now, if you're at a flight place where you're flying somewhere and you look around and you notice that maybe there's a school playground that's made of blacktop, and then over here you have the grass that's nice and cool. What you're making are little micro weather phenomena, thermals, where over here the asphalt is heating up through radiant heat and then giving off air through convection currents, making that go up, and you get over here where the grass is and it's cool. And all you have to do, where I live, there's a lot of turkey vultures. All you have to do is watch these majestic, beautiful birds flap, 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 and all of a sudden they're not flapping, but they're going up because they can feel and sense a thermal. Remember, hot air, it goes up, cold air goes down. And so if you're making any type of model airplane, knowing where those are is a pretty cool thing to do. So let me show you one more thing about air pressure. So when you go outside and look at the clouds, usually when the sky is clear, that's a high pressure. So here's my cloud in a bottle thing. So this is a fancy one. So I got a little bit of water in there. To make a cloud, you really need three things. You need air, water, and a change in pressure. So I'm going to close this up, snap it, and I'm going to pump. This is a one-way valve where I can pump, and I'm pumping air. I am increasing the air pressure because I can squeeze air, because it's compressible. I can squeeze it in here and get it in there, boom, boom, boom. And now watch what happens when I let a rapid change in pressure. High pressure to low pressure, and it should change into, here we go, check it out, a cloud. And you can see that water vapor turned into a cloud. That's cloud in a bottle. Another way you could try this at home with adult supervision is if you have a 2-liter bottle, okay, and it's got air in it, and we need something for that, that air pressure and water molecules to get on. So I'm going to put some dust, and the way I'm going to do this is let's put some water in there. So we have air, a couple squirts of water, and let me get some dust. Now it's not going to be the smoke from this. Let me get this lid here for you. And now if you do this, make sure you do this under adult supervision. And so I'm going to just start this, blow it out, and there we go. There we go. And I'm going to cap it if I find my cap. Here we go. Now, so right now we have all the ingredients for a cloud in the bottle. We have water, dust, and air pressure. So watch what happens when I squeeze this. I'm going to change the pressure. I'm going to give it some high pressure. Here we go, squeeze, high pressure. And look how clear it is. Now 1, 2, 3, when I let go, it clouds up. Low pressure, cloudy day. High pressure, clear skies. That's cool. That's a model of how clouds are made. High pressure, clear skies. Low pressure, cloudy. So, hey, don't take my word for it. Try it yourself. Or the next time you're out, look at the sky and listen to the weather models of what types of wind and what types of pressures coming through. When they say there's a low pressure, big pile of air coming your way, it's going to be cloudy. So that is a base, just a little bit start of air and matter. There's two guys that are really kind of famous that I love, and one of them is Sir Isaac Newton. And Sir Isaac Newton, I actually got to visit his birthplace in England and did the whole apple thing. I actually went into his garden, and I have on my YouTube channel a lot of videos. But Isaac Newton, who had 3 laws of motion. He studied how things move. And you need to know this because your model airplane is going to move. And so his first law says, an object at rest stays at rest, meaning unless a force acts upon it. So that means your model airplane is not going to go anywhere unless you have a force to make it go. And that might be your arm force, or it might be potential energy. Let's say you wind up with a rubber band, giving it potential energy, releasing it to kinetic energy, or it could be a battery that is stored potential chemical energy. When you turn it on, kinetic energy. or it might even be a gas-powered plane. So that is the first law of Isaac Newton. Action, the first law is that object at rest stays at rest. His second has to do with mass and force and acceleration. So basically it's F force equals ma, mass times acceleration. The more force, the more you can accelerate depending upon the mass. So think about it this way. If you had let's say you had a model airplane made out of paper that only weighed about this much, you could throw it with a big force, but the mass, it's probably not going to go far, as opposed to something that had a little more mass that you could throw it, like this apple here. So his first law was an object at rest stays at rest, unless a force acts upon it. His second law is force equals mass times acceleration, depending on what type of energy you're going to use to move your airplane. So it's pretty, energy is the ability to do work, and a force can be a push or a pull. So his third one is action, reaction. For every action, there's an opposite equal reaction. So that comes in when you're learning about propellers and torque. When a rubber band is pushing the plane this way, there's also reaction in the opposite direction. I like Isaac Newton. We studied a lot about Isaac Newton. You know, one of the things he talked about here is a planet going around the sun. It's the gravity that holds it in place. It is moving, so it has some force. And if I let go of it, wonder which direction it would go. According to his first law, it should go straight, not. We can try that. So if we did not have gravity, we'd be in big trouble because our Earth would be gone. So Isaac Newton, pretty cool. He studied light. He did a lot of things with light. But I can do, here's an experiment you can do at home real quick. This one could get you in a little bit of trouble, depending on how good. But if the science is right, it should work. So that object at rest. So here is a tablecloth I'm going to put down here. Okay? So I got my tablecloth down here. And I'm going to put something like this very heavy hammer. Yikes. And maybe I'm going to put, let's try to put this plastic container, and let's see what happens when I put this here. Let's make it really fancy. Boy, I don't know, that could be a problem. Let's see. All right, so what I want to do, those objects are at rest and should stay at rest forever unless a force acts upon them. So that's why I said it gets you in trouble. Before you try this at home, practice. Talk to your parents first. Okay, so here we go. So if I pull this, because of friction, another force of how two objects going together, very important force, the friction should be overcome. Let's see, here we go. I haven't done this for a while. Try this at home. 1, 2, 3. Tell you, when you try something that doesn't work, try it again. The variable. I think that plastic. Let's try it with just the hammer, the heavy hammer, and see what happens. Here we go. Action, reaction, object at rest. 3, 2, 1. Pretty good. It stayed there pretty good. You might want to practice that with plastic before you move on to glassware. So the last thing about Isaac Newton is laws of motion. Remember, in science, if it's a law, not a theory or not a principle, but a law is supposed to work everywhere. It's supposed to work here in my classroom. It's supposed to work at your home. It's supposed to work out on the flight zones. It's supposed to work everywhere. And so these are, I call, my Isaac Newton earrings, okay? And they should stay there no matter what, unless a force acts upon them. So if I turn, they stay. There's only one point of friction right on my head. Now, that point of friction is catching up. And so it put a little bit of force on there. See if I can go back this way. Oh, my flat head. Let's try that one more time. You can make these. I made them and tried to make a lot of money selling them, but nobody really likes Isaac Newton. You have to be a real big science nerd to like or really to love Isaac Newton earrings. So Isaac Newton, you know, during the plague, the Great Plague of London, when he went to Woolsthorpe Manor to stay away from dying, that's when he worked out the laws of motion that we use in flight, and almost every aspect of our life. He also studied color. That's a Newton color wheel. But now we're going to move on to this other scientist who is actually a Swiss mathematician by the name of Daniel Bernoulli. Now, Daniel Bernoulli was born in the 1700s, in fact, 1700, and he lived to be about 80 years old. But he came from a family, you should look this up. The Bernoullis were like geniuses. I mean, the whole family, like 27 of them, were violinists and composers, and they really learned a lot. It was like there's some smart people there. So Daniel Bernoulli, even though he's a mathematician, he came upon a discovery that he tested, and today it's called the Bernoulli Principle, a principle of things that should work. And let's see, I wrote a little notes about the Bernoulli Principle. Daniel Bernoulli. Now basically, BP stands for Bernoulli Principle. And I have pressure. Pressure is the arrow going down. Velocity is the arrow going up. So basically, that's pretty simple. What that means is when you decrease the pressure, that should increase the velocity of a fluid, a gas, or a liquid. Very simple, the Bernoulli Principle. But like I said, scientists were skeptical. So let's see if that actually does work. Let me move some of this stuff out of the way here. So Daniel Bernoulli, the very easiest way you can try this at home is if you have a piece of paper about like this. And so this piece of paper, if I blow across of it, you probably think it's going to bend down. But if I blow my air fast enough, velocity, if I increase the velocity, the pressure should change. So predict, is it going to go up, stay the same, or go down? Let's find out. It went up. Less pressure on top, the rest of the sky helped push it up. Now think about that. The pressure in this room or in your room is pretty even. But if I blow quick, that's going to be increasing the velocity of that air, and inside of that, it's going to be decreasing the pressure, and it should go up. Now, there's so many cool ways you can test that. That's the Bernoulli Principle. For example, let's try this one. This one is kind of hard for me to do, but I got a little straw, a little styrofoam, and if I blow, I can keep this going. But going straight up is pretty cool, but I should be able to turn it sideways. But you can try this at home, right? That's the hard part, going it just right. Now, I'm going to try to tip it this way. You know what? I have a leaf blower and a big ball. We can try that. Let's try that and see if I can do it. Now, it's going to be kind of loud, and I'm going to try to get it so I just barely turn it on here, and I'll see if we can get this thing going. Here we go. It's going to be loud, and I'll make the air. I'm going to increase the velocity of the air, so it should lower the pressure. Here we go. Let me turn it down just a little bit. Here we go. I'll hold it down low. That could be a problem. We'll try it again. I knew that might be a problem if I had the right size ball. Let's try this ball right here. It all has to do with trying to make a video with just a little bit of space here. Let's see what happens here. That's too much. That one is way too much. It might be easier if you have a hair dryer to try this, but we'll come back to this in just a minute here. So that was increasing the airflow in kind of a dramatic way. There's a couple other things I can show you that are not so dramatic. I like to call this one the Bernoulli Car. It's an antique car. It has no energy, but if I wind it up right now I'm giving it elastic potential energy. I let go, and it moves potential kinetic energy. But it has a little pump in there. So let's see if I can get this going right here. Here we go, try this. That's so cool. And if I turn it sideways, watch, it still stays. Even if I turn it, let's try it one more time. So let's see if I can get this. This is my Bernoulli clown car. Let's see if we can get it to go across the table. Here we go. There we go. Maybe I need to wind it up just a little bit more. This is pretty cool. Bernoulli clown car, kind of hard to find. Now, this is a prediction. This might be weird. I have a funnel here. And if I just let go, the ping pong ball goes down. But what happens if I blow? Will it go down faster? Watch what happens, then you see if you can figure out why. Here we go. Ready? You see that? when I ran out of air, it fell. Let me get a little bit more air in me. Right, here we go. It stays up in there because as the air goes around this ping pong ball, increase the flow, decrease the pressure, and the rest of the room held it up. That's the same way, like maybe I can even show you this. Watch when I blow across this. Which way do you think it's going to go? See how it went up? When I blow across the top, it decreases the pressure and it's pushed up. This one's kind of fun to try. You can try this too. Here's an empty aluminum can. And I'm gonna see if we can do the same thing by having it inside of here. I'm gonna blow across the top of this. If I increase the flow, decreases the pressure, and it should jump, we hope, into that bucket. Let's see if it works. Here we go. Ready? I'll do it a little bit, just see if it rises. Try it one more time. Here we go. That's so cool. If you press from the side, it comes up, you give it a good blow, it will decrease the pressure and land in it. It might take a little practice to do it. Here's another cool thing about Bernoulli. So here's two containers right here. Let me put these, so if I blow in between them, you probably think they're gonna come apart. But according to Bernoulli, the opposite should happen. What should happen is if I blow in between these, increase the flow, they should come together. Now the first time I'm going to do it may not be as dramatic. Let's see, ready? Here we go. Oh, they moved a little bit, but friction is stopping them from moving all along. So I'm going to put some straws. You could try this at home. I'm going to put some straws down, 3 straws here, and now I have decreased the friction. And I'm going to put 3 little straws here. I have decreased the friction, so it might be a more dramatic demonstration. All right, here comes old Bernoulli. Ready? Blow in between. You would think they would go out, but they should go in. Here we go. 3, 2, 1. You see that? They came together. That is so cool. That is Bernoulli's pressure. And what does that have to do with airplanes? Well, your models have a wing. We call this a foil. And if you notice, you probably have already studied this, you have a leading edge and a trailing edge. And the shape of this allows, as it moves through the air does actually change a bit. And as it goes across the top, the velocity is increased. And what does that tell you about the pressure? It's going to have less pressure, and the rest of the atmosphere will give it lift. And as you've probably studied in flight, there are 2 sets of opposing forces: lift versus gravity, and thrust versus friction. And you want to be able to control or work with both of those. So your foil in this shape, and oh, by the way, the Wright Brothers did a lot of math and a lot of modeling and testing. They listened to some of the other scientists and explorers, and it just wasn't working. So what did they do? Just like you would probably do, they built their own wind tunnel and tested different shapes to try to determine the best shape for their aircraft. And you can actually visit the Air and Space Museum and see that, or videos about how an airfoil works. Now, so that's how a wing gives lift, but the propellers that we use on planes are basically an airfoil that's been twisted. Yeah, it's like a wing. It's like it's going around. And so what does it do? A propeller has a leading edge and a trailing edge and is in this shape to actually cause a difference in pressure. Whether it's a fixed wing propeller or a rotary going this way, it all has to do with an airfoil and our friend Daniel Bernoulli. In fact, air, as you guys have told you at the beginning, all air is made of matter. All matter takes up space and has mass. So that's so much air from here to 50 miles up that it actually has a pretty good force. Maybe you've seen these. These are a can, and I put this with just this much of surface area, just that much surface area. I can push this down, and I can use the rest of the atmosphere to hold this up. If I can get it down just right. Push it down, push that air out. And so now I push that air out, and it should hold up this Coke can, or any of them that's as full as this. And it's because of all the air I pushed out, trying to get back in, the press of air, air pressure. And our friend Daniel Bernoulli. Now, we have a Bernoulli bag, and the Bernoulli bag, our hosts at the AMA are going to show you how to use that and how to make it. And it's named after Daniel Bernoulli. How in the world could you fill a bag like this with one breath of air? Well, using science you can. If you can increase the flow, you decrease the pressure, and the atmosphere will fill your bag. And they'll be able to show you how to do that. And if you don't have a Bernoulli bag with you, make one. Take a couple bags that bread comes in, cut them out and make you a long tube, one end open, one end closed. Make your own Bernoulli bag. I got one more thing to show you. Remember we talked about old Daniel Bernoulli and the Bernoulli Principle. This one could get you in a little trouble, but hopefully not. If I blow across this, I increase the flow, the velocity, and I decrease the pressure, so it goes up. So what would happen if I really increase the velocity? For example, I add my little leaf blower here to it. Well, let's find out. And like I said, I'm Rick Crosslin. I really enjoyed sharing my world with you about science and model airplanes. And who knows, you may be the next person to remote control fly a model on Mars. It'd be so cool. Let's see, let me get this air going. We'll see what's going to happen here. Hey, thanks for watching. Here we go. Let's get this guy plugged in, turned in. It's always a good thing to do. And I get so much trouble. One more time. See you next time. Good luck and have fun in your camp. Go outside, build, trim, fly a model airplane. Because when you fly a model airplane, you're an aviator. See you around.